BVS Pragati channel welcomes you. In this session, let's have a discussion about Hartley oscillator. Then we'll follow it up with Colpitts oscillator, Clap oscillator, and we will discuss about crystal oscillators. So in the previous session, we have seen about Wien bridge oscillator and RC phase shift oscillator. In Hartley oscillator, what we are doing, we are using the tank circuit L and CC to provide 180-degree phase shift, and the remaining phase shift is provided by this amplifier circuit. So we're using a center tapped transformer. Why are we using it? We're using it to feed back exactly the right amount of voltage for constant amplitude oscillations. For example, if you feed back more than necessary, the amplitude of oscillations can be controlled by biasing the amplifier in such a way that if oscillations increases in amplitude, what happens? This appears over here. The signal at XY is 180 degree out of phase with YZ. So this signal XY is appearing over here. So R4 is emitter bias circuit. This is actually a negative feedback resistor. So since the amplitude has increased, the negative feedback increases. What happens? Effectively, it pulls down the gain of the amplifier. Hence, the oscillation amplitude is also reduced and it regains its original value. And if the amplitude of oscillation decreases, what happens? This appears over at XY, which is seen at R4. So since this reduces, what happens? Gain of amplifier increases, thus regaining the original value of oscillations. In this way, this is called automatic base bias, and we are trying to feed back the right amount of oscillations for constant oscillations. R1 and R2 are DC bias resistors. R4 is a negative bias resistor. CE is bypass capacitor. There's a blocking capacitor over here and a blocking capacitor over here. Proper values of L and C produce oscillations. These oscillations are very low. To have constant oscillations, we are providing feedback that we have discussed now. So signal at XY is 180 degree out of phase with signal at YZ. Okay, the remaining 180 degree phase shift is provided over here, and the correct phase relationship of positive feedback is obtained. So what is the gain of the circuit? Gain is the voltage over here, which is X omega LA. So L is like LA and LB. L is equal to LA plus LB. So X omega LA by X omega LB. So it is LA by LB. And what is the feedback factor? LB by LA. And what is the frequency of oscillation? 1 by 2 pi root LC. And L is LT, which is equal to LA plus LB. LC oscillators are not stable due to variation in diffusion capacitance. Voltage gain of Hartley oscillator we have discussed is LA by LB. Feedback factor is beta is equal to LB by LA. Now let's have a discussion about Colpitts oscillators. In Colpitts oscillators, what we are doing? We are using capacitors CA and CB, and CA, CB and LA is forming the tank circuit. The voltage at XY is 180 degrees out of phase with voltage at YZ. The condition at oscillations is X omega, that is XCA plus XCB is equal to XLA. Okay, XY is 180 degree out of phase with YZ. 180 degrees is provided over here, 180 degrees is provided over the feedback loop, and total phase shift is 360 degrees, which is the required phase for oscillations, that is for positive feedback. Okay, so what is the voltage gain of oscillators? A is equal to CB by CA, and the feedback factor is CA by CB. This is about Colpitts oscillator. Let's have a look at Clap's oscillator. If you want to make the Colpitts oscillator variable with frequency, you need to add a small capacitance C3. This is very small. Okay, so in this case also, XY is 180 degree out of phase with YZ, and this is providing 180 degree phase shift. Remaining phase shift is provided by the circuit, the amplifier. So totally 360 degree phase shift is obtained. Okay, so since C3 is chosen to be smaller than the other two capacitors, F0 is equal to 1 by 2 pi root 1 by L 1 into 1 by C3 plus 1 by CA plus 1 by CB. Since C3 is chosen to be small, F0 is equal to 1 by 2 pi root L into C3. The extra capacitance will make Clap oscillator preferable over Colpitts because you can vary oscillations with frequency. So this can act as a variable frequency oscillator. C3 is chosen to be small so that at higher frequencies, larger will be XL. It also reduces stray capacitances. So that's all about Clapp's oscillator. Let's have a look at Colpitts crystal oscillators. In crystal oscillators are more stable since Q is high. You are using crystal to control the oscillations, and the stability of crystals are very high. Q is very high. It has high L by C ratio. If Q of an oscillator is high, it is more stable. Crystal oscillator has high Q of the order of 10 to the power of 6 to 10 to the power of 8. Q is equal to F naught by bandwidth, and you have a parallel resonant circuit and series resonant circuit in crystal oscillators. Parallel resonant circuit is equal to R by omega L. The stability is delta F by F naught into 100%. That is small marginal variation in the oscillating frequency into 100%. That is stability. And in crystal oscillators, the stability is very good. Stability of Hartley and Colpitts oscillator is poorer. Crystal oscillators have high stability. That's all for this session. More in the next session. Thank you. Thanks a lot, and I wish you all the best.